Thanks very much, Jerry. Good morning, everyone. So I'm just going to talk to you briefly today, give you an initial kind of overview of what the system analysis strand is all about, and then I'll introduce Paul, who's going to go into more depth, and then John from ESP will then talk about ESP Network's role in this. So system analysis and what we mean by that, our focus within the strand is really on simulation and analysis of the power system. So on the generation side and on the demand side, and also particularly on the network infrastructure itself, so what kind of ties the whole power system together. A particular focus for us at the moment in the strand is around system services, so around the services that are required for the secure and reliable operation of the power system, so reactive power, reserve, frequency regulation, things like inertial response. So we're trying to address these. And the context, I guess, which is the context to a lot of the work that is going on across the ERC and within the CEAS cluster, is the role that new energy resources such as wind or demand side can play in this. So how they change that picture, how they change the system, the technical impact, and then equally how can they be utilised, or how can other resources on the system be utilised to, as I say, maintain that secure and reliable operation of the system. One of the key things in that regard is to reconcile the overall objective of ancillary service provision, so these things such as reactive power and reserve, while also, of course, maintaining the requirements for local power quality and local network reliability. So what we're seeing here, in particular in the Irish context, is a lot of the wind generation that we're seeing connecting is, at least half of it I think, is on the distribution network. So that's a complete change, a new paradigm within power systems. And Ireland is seeing a particular, I suppose, leading edge in terms of those developments. So we're trying to reconcile the overall objective of trying to provide reserve from a high level system point of view, while also ensuring that perhaps with a local network point of view, that we're maintaining the power quality and the network reliability and respecting all those local constraints that govern the distribution network. In terms of the people that make up this strand, you currently have 7 PhD students and 3 postdoctoral researchers. Of particular note perhaps is Eric Eala, who works with NREL full-time in Boulder, Colorado, and Ellen Diskin, who's here this morning as a poster outside, who works full-time with ESP Networks and is pursuing her PhD part-time. So no mean feat, but she's certainly making a good job of it so far. And of course, there's strong interaction with many of the other strands within the cluster that we'll hear from earlier today in terms of modelling, but also some of the future ones that we'll hear later this morning and this afternoon. So what I really want to talk about now, briefly, is just some of the high-level outputs that this strand has produced over the past year or so. So in particular, Alison O'Connell has developed a new method for unbalanced optimal power flow. So optimal power flow is a kind of classic optimization method used generally on transmission systems. Alison has managed to develop a new method, one of the first in the world, where we can now apply these principles to unbalanced networks, so multi-phase networks where there's unbalance present. And what that means then is that you can then model and look at the optimal power flow problem on residential distribution networks. So where we see electric vehicles increasing demand side response, we can now model those networks, and we feel that it's going to provide in many ways the engine for future smart grid control. So if you start thinking about residential networks and how do we optimize the dispatch and control of distributed energy resources, it's this kind of computation method that you need to drive those kind of future methods. We also look at the planning of the system with regard to voltage stability, and again using optimal power flow. When we developed, what staff at Backfire has developed, is multi-scenario, so it captures the variability of demand and wind generation, which is a key factor. Also considers n-1, so contingencies on the system, and provides a solution to these factors in a single execution of the problem. So it's a non-linear program, and this is not an end in itself, but it's an optimization with 280,000 variables, so of significant scale, and to the point whereby the solvers that we're using, which are developed by Sandia Labs in North America, are now asking us, how are you doing this, what's your formulation? They're trying to work with us to actually use what we're doing as a means of developing their solvers themselves. So the point of all this, of course, is that by achieving this solution, we can then tackle an increased range of questions and provide an increased range of solutions and answers, perhaps, to some of the technical challenges that are arising on the system. Next up is a new platform which we developed, which essentially enables an interface in real time or very close to real time between different simulation platforms. The relevance and key aspect of this is that it provides, I suppose, or allows us to capture the power system and control interactions in greater detail. So again, if you think about smart grids, to use that word, or intelligent energy systems, increasing amounts of control, increasing amount of controllers, how do we capture those interactions? And capturing, I suppose, the dynamics and the time constants of these controllers is particularly key. And this platform that we've developed and are developing is going to play a key role in that, we feel. Some other outputs, briefly. ECNA Fatal has been looking at identifying critical buses for system stability. So when we consider our transmission system and how do we plan it and how do we consider the effect on the stability of the system, we've identified, we developed a method by which we can identify critical and key buses within the system, whereby they are particularly important and have a very particular impact on the stability of the system. So potentially a very valuable source of knowledge for system operators to potentially improve the planning of the systems, in particular, of course, with the delivery of our renewable energy targets, trying to achieve ever increasing penetrations. And finally then, the festive unit commitment tool, which is developed by Eric Ela and James Ryan, which is a rolling intraday commitment and dispatch tool. So without going into too much detail, essentially what this tool can do is it can do the classic unit commitment generator scheduling problem, but it's now capturing dynamics right down to governor timeframes, so right down to seconds, back up to hours and days ahead, and trying to capture and optimize those dynamics and essentially the scheduling of the plant on the system. I want to get into a little bit more detail now, but just before I hand over to Paul, and one of the key things that we look an awful lot at within the strand is reactive power. Megavars, they're kind of ubiquitous on AC power systems, and it's the focus of a lot of our work. So just very briefly, Mario Jamaria from Croatia, one of our PhD students, looks at this with regard to how to optimize distribution network planning, so how to optimize the integration of renewable energy resources on the system, and particularly utilizing reactive power as a means or a method of optimization. ECNIT, who I mentioned before, is looking at transient stability of the system, considering reactive power control, highlighting that it's not only voltage that is relevant to reactive power, but it's also the rotor angle stability of your existing machines. Mustafa, as I said, is also looking at system planning, considering voltage stability, looking at that large-scale, multi-dimensional optimization problem. And Paul, who I'll hand over to in a minute, is considering the reactive power resource characterization. So if we think back to the fact, as I mentioned, that wind farms are connecting to the distribution system, we now have a lot of distributed generation. We have a lot of distributed reactive power resource out there. How do we characterize that? How do we consider that within our planning methods, both on distribution and also on transmission? So that's something that Paul's going to talk about more. And equally, we're very, I suppose, eager to do work trying to quantify the actual real impact of these these factors. So reactive power, or imaginary power, as some people call it. We're trying to really, I suppose, deliver the next step, saying, well, here's the impact on stability, but what actually does that mean in terms of euros, or what does that mean in terms of the reliability of your system? So without further ado, I think I'll hand over to Paul, who'll bring us through in a little bit more detail some of the questions around the role of reactive power.
Thanks, Andrew. Just a little bit more detail. I don't intend this to be a fairly, cursory little look through some of the research, past and present. I'll just start with something that's fairly intuitive, I'd hope. This is a kind of stylized view of a test network, the IEEE Reliability Test System. You can see here, this is the flow of active power to this network, so it makes sense. We've got these red generation nodes, they're supplying active power, then flowing out to the system to all our blue load buses. So, it's this view of the power system is what is typically underpinning any kind of economic analysis. This is what's behind unit commitment and dispatch and everything like that. This particular flow, which is fairly easy to quantify in a fairly linear way to do with the reactances, the lines, and the voltage angles. But at this exact same moment in time in this power system, we have this other flow, the reactive power flow, which generally doesn't get looked at from an economic point of view, where you've got different sources of reactive power and different sinks of reactive power. So some of those sources of reactive power are generators, because conventional synchronous machines, you're burning your gas to produce your megawatts, but at the same time, you get to produce reactive power effectively for free, which is kind of a nice coincidence. Then also you can see here down this load bus called Alber. That has what's a dedicated reactive power device installed there, where you spend capital expenditure to put it in to produce reactive power. So basically, because we've got this flow to the network, I won't go out on the network anymore, because we've got this flow in the network of reactive power, it affects everything. So Andrew was talking about the different bits and pieces of research we're doing. It affects congestion, it affects the voltage levels. Now, one of the things that I'm interested in is kind of looking at it in a holistic power system point of view. What's the transmission system operator's perspective on reactive power? What's the distribution system operator's perspective on reactive power? So for the transmission system, it's about stability. It's about maintaining acceptable voltages everywhere, even under contingencies. For the distribution system operator, maybe it's more about managing losses. It's about accommodating more generation onto a section of distribution network. So I'm going to talk first about some of the transmission system implications, then move kind of how to be harmonized what the distribution system needs. So this is actually the same network that I just showed there in a more conventional single line diagram kind of a layout. Not to get into too much detail, it's a well parameterized test system, so it gives us the electrical data for the system, as well as heat rate curves for the generators, which is kind of cool because it means we can now examine the system from an economic and an electrical point of view, which some people don't do quite enough of, in my opinion. So what we did is we connected enough wind into the system to get 15% energy penetration over the year. We're assisting this by EPRI, Dr. Aidan Tui and EPRI helped us in this, and Eamon Lanoy, who at the time was with the ERC, now is with EPRI, to basically do the unit commitments portion of this work so that we could have real economics behind it. It was good to be able to sort of draw on that interdisciplinarity within the group. So anyway, the take-home bit is that we found we connected all this wind, this 50% wind, in a very crude way to sort of simulate what a distributed network might look like in a certain sense. And this is what happens. So 15% energy from wind over the year. There's going to be hours when you've got quite a lot of wind. At those hours, you see very poor voltage. You can see the voltage is dropping away there. There's sort of outlier points where you've got very low system voltages, median voltages across your system. And that's because you're not doing an intelligent strategy to harness the reactive power you could get from the wind. So we said, well, what if we enable voltage control, which is the most obvious way to use that reactive power that modern wind farms give you, and you find, great, your problem goes away. You can now have high penetrations of wind, and you don't get those depressed voltages. Now, the interesting bit is that if you instead decided to fix that problem using your conventional generation, so to impose operational constraints, so you'd have regional constraints that you'd say to fix those voltage problems, we'll make sure we have a conventional plant in the right place at the right time to provide that reactive power. That distortion that puts on your commitment schedule added 8 million in this test year, so 3% extra on your operational cost. Now, it was a fairly crude metric, so I'm not saying 3% is the figure, but it does show that if you fail to manage your reactive power well, you're either going to spend extra money on operational constraints or on capital expenditure to fix the problem. So there is, a real concrete reason why you want to manage your reactive power. So, what that bit of work, shows, and it's really just a little kind of worked example or allegory, says that, it is possible to get reactive power from distributed wind, and if you do, this is a benefit for the whole power system. So some of the previous work is involved in that Andrew alluded to was about kind of characterising that resource. If you have these wind farms in a distribution system, and modern wind farms can provide reactive power, how do you kind of aggregate that together so you get a handle up at the transmission level of what's going on in this big, long, complicated, stringy section distribution network? So not to get into the details, but we came up with a technique involving some new optimization approaches. So you can take a big distribution network like what's up there, where you've got load and you've got a lot of buses and you've got various generators with various characteristics. You can make certain assumptions and say, if we know the reactive power that those generators can provide, how much can the whole network provide up to the transmission system? So how do we aggregate that together? Kind of like a virtual power plant kind of an idea. And it turns out that the reactive power you get depends on the active power flow. This is a key thing at distribution level. The two flows are kind of entangled. The initial diagram, what they showed for the transmission system, they're kind of two separate things going on. For distribution systems, they affect each other. So as the active power output increases from this network, the wind goes up, the whole network starts to export active power. That kind of cuts into how much reactive power you can provide. So from this, we're kind of saying, we're at a position of saying, okay, we know there's a resource there. We can go some way to characterising it, so we can feed that into planning studies. We know there's some value in it, but what's the best way to actually use it? What's the best way to harness that resource? So we got some inspiration in this respect from a project we're involved in, again with EPRI and with ESB Networks, trial project, certain distribution system, dedicated generation, just 2 wind farms on it, and looking at ways, if we were to enable voltage control for these wind farms, what kind of behaviour would that give us? So what you find is, this is the 2 wind farms, and over a 24-hour period, you can see that they're varying their reactive power in what turns out to be quite a useful and coherent and sensible way, instead of having it fixed at a kind of power factor value. So because the wind farms are actually naturally controlling their own voltage, it turned out that it meant, traditionally in distribution systems, you have what's called a tap change transformer, which sort of sets the voltage throughout the distribution system. But when you're kind of operating your network a bit backwards in a certain sense, that you've actually got voltage being controlled at the remote end, it means that your tap change becomes a lot less important. We kind of find through this trial and related work that you often don't need your tap changer so much, which is kind of good news because you've got less wear and tear and less maintenance. You mightn't even need to specify the tap change to begin with. So there's a potential big benefit there for the distribution system operator that an intelligent voltage control strategy can save them money. So because of this, we're saying, okay, it seems that there's potential for some synergy here. And that I was saying, how do we harness this distributed resource? One of the main things a transmission system operator is interested in with reactive power is controlling their voltage. That's effectively what reactive power is for, the transmission level. And what you want is, ideally, a kind of sensible organic response that, if at a particular point in your transmission system, for whatever reason, your voltage starts to drop, what you want is an injection of reactive power at that point, and that will have the effect of lifting the voltage back up. So this keeps your system a lot more stable and secure. So that kind of organic response, we were interested in saying, can we get that without needing central dispatch or complicated control schemes or complex telemetry? If we can get that in a natural way, then it'd be ideal. And this is the idea of locking the tap. If we can take that tap changer out of the question of the interface between transmission and distribution systems, the idea would be the transmission system voltage, say, will drop, and because that's directly coupled through the distribution system, there's the generators there are naturally exposed to that and will naturally offer up their reactive power in response. So the idea does work. It turns out to be kind of tricky to implement, so we went back to that fantastic Swiss Army knife of AC optimal power flow. So basically, there's an example in this small network. We haven't quite got out to the big load networks because the question becomes pretty big. But for these 4 generators in that transformer, in an optimal way, you can select their voltage control settings and that tap setting to kind of get this aggregate response again, which you can kind of see, as the voltage tends to go down at the transmission level, that tends to summon up a reactive power injection, which is the sort of thing you'd want. And also it's kind of balanced between plus or minus 15 megavars. This mightn't look very impressive, but when you're trying to do this by hand, it's very difficult. It's great that the optimization actually gives you this answer. So that's kind of hot off the presses. This is what we're looking at right now. So we've kind of moved from a characterization to a use kind of question. So basically what this is about, is why are we looking at reactive power in this way? Like I said, if you don't have good reactive power management, you're probably going to have some cumbersome operational constraints, which are going to distort your merit order. It's going to cost you money in that respect. If you have better reactive power management for the distribution system operator, one issue is you have less reliance on these tap change transformers, you have less wear and tear. I haven't really discussed it here, but potentially you can accommodate more generation in a certain network section. And whether you're a transmission or distribution system operator, you can probably save money on investing in these dedicated reactive power devices because you've already got a resource. It's sitting there in a modern wind farm, so you'd be mad not to use it. So both sides of that are saving on capital investment. So that's all I have to say.